do that. So, for example, if an explanation is complete, that is to say, it has the contrastive property, are the humans being able to identify whether the plan being explained is optimal? So, the completeness property says that in the updated model, the plan would be optimal. Are the humans being able to identify that? In explanations where that's not the case, are they being able to identify that the plan is not optimal? So, do the explanations have the kind of behavior that we try to model?
Just a quick question. So what would be the optimality criterion here? Could the human have a completely different idea of what optimal is?
Yeah. So it's in this case it's the shortest plan with the double removal actions. So if the human can see another plan that they think that it's shorter or has less number of steps, then that would be suboptimal.
But in experiment, did you tell it the human?
Right. So it's in the
Why are these the only explanations that are possible?
They were not. So in the in study 1, where they were given so there was no limitation on the communication. They did point out other types of explanations they would like to give, and so those would be in terms of say foil based. So cost between two plans is different. Some people actually wrote about explanations that become valid on execution. So if you went through a wall, you don't have to explain that there is no wall there. So defined explanations from the ones we looked at in the free-form case, but in the low communication case, most people went with.
I guess I'm asking a slightly different question. So what I'm asking is, your answer is more in terms of how you evaluate it, right? But I'm asking in terms of the hypothesis itself, why is it that MC, PPV, MPE are the only reasonable types of explanations, right? I mean, to make up a pathological case, I could say humans seem to prefer robots that are blue rather than red, saying things to them, right? So, I mean, I was looking at the thesis. It's not clear that you have cited any past work on, these are good explanations versus these are not. So how did you come up with these explanations as against others, that might be just as relevant to plans?
Oh, that's right? So these are not the only explanations out there, right? But in the limited communication case, those were the ones that they favored. So
what are the other ones?
So the other ones would be, for example, looking at two plans and explaining the cost differences. That's not a model difference explanation. It's a difference saying that this in the same model, this plan has more cost than this one. Then there's the other one on say based on execution, you can choose not to give model.
And did you evaluate those with you?
No. So we were evaluating that if these explanations are useful and under what circumstances. So in the subjective studies, we didn't put the subjective studies for this, but they are in the thesis. We did ask them whether they found them either necessary or sufficient, and most people agreed that they were. These kind was necessary and sufficient. Yeah, and so this one was about the humans evaluating the explanations, not generating them. And again, we found that in most of the cases, they were able to identify the contrastive property of those explanations. One interesting outcome was in terms of how many times they were asking for explanations for plans that were explicable. And it seemed there is a significant decrease in the number of times they asked explanations. So that's the red mark. So that's the percentage of times they ask explanations given an explicable plan. So even though it's much less, there is still a significant amount who did ask for explanations for explicable plans. And one of the reasons for that might have been the high stakes nature of the environment. So it's such an environment you want to make sure that the plans are successful. The setup was also gamified in the sense that invalid plans will be penalized a lot. So they might have been discoveries in asking for explanations. So that's about the explanation and explicability trade-off in considering the human mental model. So in the third part of the talk, we'll talk about communicating between the human and the robot if we have access to these models. And so this is work that I have done this year, mostly post-proposal stuff. And the idea here is that if we are able to make human-level plans, we still want to communicate to them. parts of our behavior. Right? So one reason for communication is that to actually give your explanations to the human. So that requires channels of communication. But also, if the models are completely reconciled, there might be still many plans that are possible given a planning problem. Right? There might be many optimal plans, for example. So just because you know the right model, the goal and the initial state doesn't mean you know the plan. So the point of communication here is one, to be able to communicate the explanations, but to also communicate or foreshadow what your future behavior is going to be given these models. So the key problem in interacting with between humans and machines is the impedance mismatch between how they represent information and how they communicate between each other. So for example, the robots cannot directly provide the internal state to the human, and the human cannot directly infer the robot state either. So there is a communication barrier from both sides. And the problem with natural language is that it's often ambiguous. And so the same sentence might mean different things in different contexts. And oftentimes you don't need the entire explicit the capabilities of natural language. So if it's an engineered setting, imagine it's a manufacturing setting, semi-autonomous manufacturing settings, we don't need natural language to interact with robots. So in this particular work, I looked at emerging techniques in augmented reality and to see whether we can find more effective channels of communication based on visual cues in mixed reality. So what this kind of setup will look like is that there is a real workspace, and in the usual case, and there is a augmented workspace overlaid on top of the robot, which allows the human to interact directly with the robot in terms of the visual cues. So it can have direct access to the robot's control panel, but it might have other visual cues that it can interact with that can shape the behavior of the robot. So there has been a bunch of previous work in the robotics community at looking at these alternative forms of communication. But mostly it has been from the context of motion plans. So trajectories and different motion behaviors of the robot. So in this work, what I wanted to see was how can we use mixed reality to facilitate long-term planning and execution. So the three ideas that we looked at. So first, we looked at the execution time behavior. So if you're executing task plans, how can you disambiguate intentions at the time of execution? We looked at the idea of generating plans that are easier to disambiguate. So in the first one, it's only at the time of execution, but in the second one, we are asking, can we use that in the generation process itself? And thirdly, the idea of achieving common grounds in the form of explanations through these visual cues. So that's closer to the model reconciliation kind of setup that we talked about. So the first step towards achieving this is to be able to identify domain-independent vocabulary that we can use in many different task planning problems. And the two kinds of communication actions that we came up with is this idea of action projection and state value projection. So the idea of an action projection is that you are going to project a symbol that's associated with a particular action in the domain. So that means that action is going to appear at some point in the plan in future, but you don't know when. Same with the state value projection, where we are projecting a particular value of a variable in the environment, and that value will take that variable at some point in the plan in future, but again you don't know when. So that's the very basic vocabulary that we will use. And of course the limitations here is that you don't capture sequentiality here. So if you project two action value projections, then you know both those actions will happen at some point in future, but you don't know the order. But the good part is that this is domain independent. So given any task planning domain, you can have these kind of projection actions. And you will see that even though quite limited, this can allow us a very rich set of communication possibilities. So execution time projection, what does this look like? So here the robot has a plan that is going to execute, and the human has a set of plans that the robot thinks, that the human thinks the robot might make. So at the execution time, the robot has to figure out what are the salient features of his plan that it can foreshadow to the human, and that will allow disambiguation among all these future plans. So to do that, we go back to this idea of resource profiles that we talked about at the beginning of the talk. So we compute the different profiles of the features of the plan that we are interested in, that we want to disambiguate from the set of possible plans, and also the one that the robot is executing. Find the overlap between those profiles and find the most disambiguating features and use the projections for them. Right? So we try to find the profiles for all the green plans, the profiles for the blue one, and then compute the result. And then we display, in this case, the projection symbol corresponding to this future action is going to disambiguate all the possible future plans. So that becomes the projection action. So what this would look like, so in this case, this is a word building domain, and the idea is to project to the, so the idea is to project to the human what the future word will be, but the robot has only actions of individual pickup. So it's projecting in terms of those individual pickups. In this case, it's projecting an arrow on R, and R being in only one of the possible words, given the projection that the R block will be picked up at some point of time, the human can tell that that's the word that the robot will end up in future. So in this case, that's the most discriminating future action, and that's being used for projection. But the video is not that. Yeah, so in this case, so the projection appears as a small bobbing arrow, pickup arrow on the block. But this only solves part of the puzzle. Like, so because full disambiguation might not be possible. Given a set of feature plans and your plan for execution, it may not be possible to find one or a set of projections that will fully disambiguate the future plan, given the limited set of vocabulary we have looked at. Also, even if it's possible to disambiguate, the human may not like what the future plan is. So they do have the ability to come back and interact with the projection. So in this case, the robot has projected this particular future action, and the human can come back and say, that's not what I want. And that allows the robot to replan around that action and complete the plan. So this is a case where this kind of interactive replanning is happening. So the robot here has the task to build a tower of height 3, and so it is projected pick up and not available options on the different blocks. And the human pinches on one of the blocks, says that's not what I want, and the robot replans and uses a different block to complete its code. So the idea here is to allow the human to use these visual cues and interact directly with those visual cues instead of using natural language and going through possibilities during execution. And of course, you can use these visual cues to do a bunch of other things, like showing area of use, find hidden objects, etc., which has been done before as well. So far we have looked at this idea of disambiguating intentions at execution time. What if we can use this capability in the generation process itself? So we want to generate plans that are easier to project in future. So what this would look like is, so we have the same setup here, but now this is during the process of search. It's not at execution. And at a node in the search process, we are trying to figure out what action should I take so that this decreases the entropy of the probability distribution over future plans. So in this case, we are looking at the possible, in this case there are two possible actions, and the robot is trying to figure out, given the projection actions it has, which ones are better options. So the cost function is now not just the cost, but also the entropy of the possible plans from a state. And the sad part is that's very hard to compute, because then you have a number of individual planning problems in each node of planning problem. So what we did was we looked at a membership function to find a proxy of what the actual distribution is. So we looked at the set of possible plans that are possible from this state, and looked at what projection actions we have, and looked at the membership of the projection actions in each possible plan. And that gives indication of how disambiguating each membership function is in the set of feature plans. And that gives a more tractable proxy to the interrupt function. So the cute part of this is that you can use this setup to trade off the cost of the plan with the ease of communicating that plan to the human. Right? So you can, in this case, produce plans that are longer but easier to project. So this has parallels to the balancing explicability and explanation concept as well. Here you are trying to balance the trade-off between the cost of the plan and the cost of communication. And so there has been previous work on this sort of a setup where you're using your actions to make future plans predictable. So in this case, the advantage of using misstated projections is that these are not physical actions. So you don't have to bear the cost of having actions that have implicit effect on the human mental model. So you are being able to foreshadow intentions before they happen, and you have no cost of being able to foreshadow them. So again, in this case, well, the thesis has details about these individual setups, but the idea is that here the robot is going for a longer plan, in this case with the letter R, because the R is appears in only one of the possible words. And then you can adjust the value of the trade-off and actually make the robot do any one of the blocks, depending on whether you want the robot to make shorter plans versus reduce the amount of complication. So, so in both of the examples for projection-aware execution and generation, we looked at a given model that both the human and the robot agree with, and then tried to disambiguate based on that. Of course, we can use these kind of projections to facilitate explanations. As we talked about previously, the model reconstitution process can be facilitated with the use of mixed reality projections. So, as previously, in the model reconciliation case, we started with an inoptimal plan in the human mental model, and the idea of the model update would be to come up with an updated model where this plan becomes explicable. And so the model update here is the one that we want to do in the mixed reality channel. So, for example, in this case, so the goal of the robot is to make a tower of height 3 with the red block on top. And so the expected plan, or the explicable plan in this case, is that it will put down the red one. So it will put either the green or the blue block on top of each other, and then put the red one on top of the two heights. So, however, the plan that the robot comes up with is a much longer plan that does not use the red block. It unstacks the red, does not use the blue block. It unstacks the red block first, and then completes the plan. So, given the human's mental model, this is not something that's explicable. However, if you use annotations on the objects in the domain and say, for example, in this case, the blue block is not reachable, then this plan is the best that the human can come up with. And so the idea is, so in this case, this is the model update or explanation. And given this explanation, the rest of the plan is updated. So in the mixed reality channel, so that's what's happening. The robot has projected a not reachable symbol on the blue object, and that makes the rest of the plan explicable. So in summary, we looked at 3 possible kinds of interactions in mixed reality. We looked at this idea of disambiguating intentions at the time of execution, using that during the generation process, and finally using the same kinds of communications for achieving common grounds in the same notion as model reconciliation. Of course, the mixed reality interactions are not specific to human-robot interactions only. So we have been exploring other kinds of interactions, for example, between cars or between addition support agents. And so in all of these cases, we are looking at how mixed reality can improve the kind of communications that, that humans and AI agents can have. And of course, the communication is not restricted to mixed reality. There is traditionally you can think of speech and graphical interface based channels as well, and so I have somewhat along those lines as well. But in this particular talk, I focus specifically on the mixed reality part. But yeah, so I did look at different kinds of communication channels and how they can assist in human-aware AI. So coming to the last part of the talk about wrap up of the different topics that I looked at. So the key ideas in the thesis are based on this idea of being able to deal with 3 different models in the planning process. The classical one, where the agent considers his own model. The human task model, which allows the agent to anticipate joint action. And the human mental model, which allows the robot to understand how his actions will be perceived by the human in the loop. We looked at this idea of explicable and explanation generation from the point of view of this mental model. We also did human factor studies to understand how they respond to this kind of human awareness. And I also showed how emerging technologies in mixed reality interfaces can assist in the cause of human awareness. Yeah. So the examples in the talk were on this mock search and rescue scenario. But I have a parallel thread of work that looks at how these ideas translate to this to the concept of decision support, where the human and the planner are trying to make plans together. And many of the ideas that I talked about in the human robot interactions do carry over to the idea of decision support as well. And that's very interesting area of application of human aware planning. And of course, most of this work has been presented in different conferences. In particular, the ones I presented here are in green and red. The green being what the current work that I did this year, and the red are on the human task model and human mental model previously. And the work has had a lot of impact, including around 400 citations. There are various workshops that we have co-organized in the past, and also different awards from different organizations as well. So I would like to end the talk by saying thank you to my committee members and my friends and colleagues in the lab, without whom, of course, this work would have been possible. And of course, a thank you to ASU and IBM as well, who have supported my research for 5 years. I would like to end there.